Welcome to EELE 371, Introduction to Microprocessor Hardware and Software. The other nickname for this course is Embedded Systems Design. My name is Brock LaMeres and I will be your instructor for this fully online course during the summer of 2022. The goal of this video is to give you an overview of the content of the course that we're going to be covering, and then give a little bit of background on myself as the instructor and the voice that you'll hear in all the videos. And then finally go through the logistics of the course, such as the syllabus, schedule, where everything is located, so that you know exactly what to do after this video ends in order to start working on the course. Okay, so let's start with what this course is all about. So this course focuses on how to program a specific type of computer, but it's not just programming the computer, it's learning about the low-level hardware of what we call an embedded computer. Okay, so when you think about a general purpose computer, this is everything that you're probably used to, such as laptops and workstations. So this is like a Mac or a laptop, a Windows-based laptop. And this is also like servers that run the internet. And more recently, even kind of a smartphone could be considered a general purpose computer. But general purpose computers are basically designed to have an operating system that runs all the hardware, and then you can install applications on it that are specific for some particular task. Okay? General purpose computers are kind of a jack of all trades. They can run any arbitrary software. But one of the downsides of that is that they have to support any and everything that could ever possibly be done on them. So a lot of the times the computer hardware is unused for a particular application. So there's very few applications that stress the entire breadth of all the hardware that's in there, but they can do anything. On contrast to that is what we call an embedded computer, which is the billions of little computers that are in every electronic device that you have. So the microphone I'm talking into has a little computer in it, okay? The speaker that I'm listening to has a little computer in it. But these computers obviously aren't running Windows, and they're not running Mac OS or iOS. They're just dedicated computers that perform a specific task. And these are called embedded computers because they're embedded within the system they are controlling, but they're also very dedicated. Okay, so these type of computers exist in home appliances and office equipment. They're the ones that are in cars. Your car might have like 60 or 70 different computers. They're not all running Windows though. And so these are a specific type of computer. So what we do when we learn to understand computer hardware is we start learning about embedded computers because they're a little simpler. It's still the same concept of a regular computer or a general purpose computer in that it has a CPU, central processing unit, that can execute a set of instructions. It has program memory that you put the instructions in a particular order to implement an algorithm in order to accomplish a task. It has data memory, which is used for temporary storage, and then it has I/O to get the information to the outside world. All computers have that, okay? It's just that general purpose computers tend to be a lot bigger and have a lot more hardware resources to support an operating system, while embedded computers do not. Now, we learn about embedded computers because we can get down to the very lowest level of the CPU, and we can move information in and out of memory into registers, and we can watch operations on that information. Like when we add two things together, we can see the binary result, and it allows us to learn about computer hardware in a very low level way, and that's good. But while we're doing that, since it is a computer, you have to tell it what to do using software. So we start by programming the embedded computer almost at the 1 and 0 level. We use a language called assembly language, and it's actually instruction by instruction. And so we kind of start learning how to program a computer in assembly with the goal of understanding the hardware. But lo and behold, we also learned how to program in assembly at an instruction level. And then we move up to a higher level language such as C in order to implement more sophisticated algorithms that are a little bit more abstracted from the hardware. But at the end of it, you basically have learned about embedded computers, and that will help you understand general purpose computers much better. In addition to, there are people that just want to hire embedded computer programmers. Okay, so people are like the aerospace industry and the military industry, and basically anybody that creates electronics needs embedded computer programmers, so you'll actually have a tangible skill. Okay, so that's kind of the overview of what we do in this class from a content level. We break this class into 15 different modules. So the first one is just an overview of embedded systems, basically just what I talked about. Then module 2 is a digital logic basics. This is a large chapter and it covers everything that you probably have run into in like a logic circuits class. And the hope is that this is the prereq, okay? So if you look at module 2 or chapter 2 and you say, I've never seen any of this stuff, you should not take this course because we need you to have already understood, or we need you to know what an AND gate is and what a register is and what binary numbers are and what a carry bit is. All that stuff should have been covered in prior classes. When we get to this class, we're going to be programming the embedded computer, and we need you to be able to understand that when I do an AND instruction, you know what that means already, okay? So then module 3 is an overview of computer systems, all the main comparts of it. Then finally, we get into module 4, which is where we look at the specific computer that we are going to program in this class, which is the Texas Instruments MSP430. This is a beautiful little computer. This is a very widely used microcomputer, and it is awesome. It has everything that all computers need. It's not too much, it's not too little, and it's cheap. It's $10-12, and it's got all this capability on it to do what we call debugging. So we can go into our program and we can step it clock by clock. We can look at all the registers. We can do all this cool stuff with it. And it comes on a little board that's a red board called the Launchpad board. And it has a couple LEDs, and it's got some buttons, and it's got pins, and we can do all this cool stuff. So it's a great little learning platform. And once you learn it, you'll be like, holy cow, I can use this for everything. You'll probably use this in your senior design. You'll use it for hobbyists. You might even use it in your final job, okay? Then what we do in Module 5 is we start looking at how to actually program the MSP430 in assembly language. So we go through the instruction set and how you actually get started doing that. Then we start working through instructions. So we have 3 modules, 6, 7, and 8, that just go through all of the types of instructions that a computer can execute. So we do data movement instructions where you move information in and out of the CPU from memory, between memory locations, moving constants into registers, etc. Registers to registers. Then we move to data manipulation instructions. So this is like where you're going to alter data. So maybe you add 2 pieces of data together, maybe you subtract them, maybe you AND them, maybe you clear a bit. And then finally, we do program flow instructions. So this is where we're executing instruction after instruction after instruction, and then maybe we want to jump over an instruction. Okay, so we hop over an instruction to selectively execute. Finally, we have all the basics of what the computer's doing, and then we start adding in access to the outside world. So we start with our first, what we call peripheral, which is digital I/O. So essentially pins on the package where if you write a 1 to it, the pin will go high. If you write a low to it, the pin will go low. And we start like driving things to the LEDs and readings from buttons, okay? Then we come back inside the CPU and we look at the stack and subroutines, how those are implemented. And then we look at the concept of interrupts and how you write interrupt service routines. And then we look at another peripheral called a timer, where we can actually have a separate device that'll track time for us. And then, yeah, and so everything through Module 12 is done in assembly language, okay? And so it's, okay, great. Module 13, we switch over to C. And in one chapter, we will be able to do everything that we've done in the book in the first, 12 chapters, essentially, in the language C. And you'll see that it's a little bit easier, but you also don't have as much control over the hardware. And so it's really cool to see the transition to a higher level language. So then we wrap up the semester or the summer by looking at the final 2 peripherals, which are the serial communication peripheral and also the analog to digital converter peripheral. We don't cover every peripheral there is. There's a lot more peripherals that exist on these types of computers, but by the time you get through all these, you'll understand what a peripheral is, and if you need to use another one, it is pretty quick to pick it up and to learn it. Okay, so before we go on to the course logistics, let me give you a quick background on myself. So I've been a professor at Montana State University now for 16 years. I teach and do research in the area of computer systems, so programmable logic design, logic systems, digital systems, and embedded computer design. Prior to this, I worked for Hewlett Packard for 8 years, where I was a R&D engineer. I designed electronic test equipment for the semiconductor industry. So our customers were Intel and AMD and IBM. As they built new CPUs, they needed test equipment to make sure that they would boot up right. And so did a lot of work there. I did a lot of hardware design. So I did a lot of embedded computing, a lot of assembly language programming. I did FPGA design, did printed circuit board design, cable design, so all sorts of stuff like that. Once I came to MSU, I teach all the digital logic courses. So I teach obviously embedded system design. I teach the intro to logics, logic design, digital system design. So all computer engineering related courses. And then I do research in the area of computer engineering. So my research area is in the field of reconfigurable hardware. So how do you take advantage of being able to reconfigure hardware in real time to get a more optimal system? Okay, and so we actually came up with this application for NASA where we can basically build a computer that goes into space, and if it gets faulted by radiation, so radiation hits electronics in space and causes ones to go to zero and zero to go to ones, and we came up with a way to elegantly recover from that while not allowing the computer to crash completely, and we call it RADPC. And this is what I've been working on for almost 14 years. And so kind of scroll down here. We've taken a prototypes of this computer and we've flown it on sounding rockets, which is where you just go straight up and straight down. We've flown this on, let's see, where are some better pictures? We've flown this on, kind of scrolling up through here, you can see me, my graduate student. We've put this on the International Space Station. There's actually 2 of these computers up there right now as I speak. This is in 2017. They were installing a third payload that we had developed. You can see the crew member is spinning this around in space. And then we've done small satellites. So these are about the size of a loaf of bread. So as I speak, there's actually 2 small satellites in orbit and 2 payloads on the International Space Station. So there's 4 rad PCs in space right now. And then we've done balloon flights where we'll actually take a rad PC and float it around for like 100 or 200 hours at 100,000 feet and test it up there. And then finally, 2 years ago, we got the big call from NASA that we were selected to go to the surface of the moon on a commercial lander. And so in 2014, we're going to bolt one of these versions to a uncrewed lunar lander and travel to the moon and operate on the moon for a while and see if we can withstand the harsh radiation environment as we exit the Earth's magnetic field. And so this is pretty awesome. So that's my background. Just kind of give you that background to show that it's like this class isn't something that I just was assigned, right? I mean, this is my area of passion. This is the stuff I used to do. This is what I went to school for. I got my PhD from the University of Colorado in this area. I work for Hewlett Packard doing this stuff. I teach this stuff. I do research in this stuff. I mean, I write books in this area. So this is what I love to do. And hopefully you'll develop an equivalent love of embedded systems. Okay, so let's get to the course. It all starts with Brightspace. So if you go to ecat.montana.edu, you're going to find the website for the course. This over here, you'll see announcements in this area. And then if you come down to this bottom right area, you'll see this widget that has all your courses listed. You go into our microprocessor hardware and system. And what you see here is across the top, you got all the tools that are available to you, and then the weekly announcements. I'll post an announcement every Sunday to kind of just give you a quick reminder of what we're going to be doing that week and some of the deadlines that are coming up. But you'll see that the syllabus has the most detailed schedule in there. So you want to make sure, this is just a reminder, make sure to use the syllabus. You are going to have a portable lab kit that you need to pick up or get shipped to you. So right away, email me and Deb. I've sent a few emails, so you should know who Deb is. Make sure you get this kit because you're going to need it right away. You're going to do all the labs remotely. We'll talk about that in a second. And then there's deadlines due the first week. Okay, so we got to make sure that you get going right away. You can go to the next page by clicking here, but really, content is where you go for everything. So all these tools are fine, but they're all linked within content in this course. And so if you go to content, you'll see here are all the pages for the entire course. Starts with course information and syllabus, and then you see module 1 through module 15, and we end with a final project. Okay, so what does a typical page look like? If I go to course information and syllabus, right here you'll see this is the red board that you'll get in your portable lab kit. And then you come down here and you'll see some links to the syllabus and the overview video. And then you have a course overview quiz, which is your first assignment. Very simple, just to get you into the system. And then you come down here and here's your contact information. I'm in Norm Asbjornson Hall. Email is the preferred mode of communication. And here's my WebEx room if you ever want to chat. But the big one is Connor. So Connor is our teaching assistant. Connor is the man. He is going to be your go-to person. Okay, so Connor's doing all the grading. You always want to be nice to the grader. Okay, have a good relationship. He's also, since he's grading, he's on call. Like he's the guy, he's being paid this summer to be the TA, so he's available to meet, to help at any time. Okay, so make sure you use Connor. He's your go-to person. Since email is the preferred mode of communication, actually you have a little extra credit assignment right away that if you want to read this professional email etiquette guide and then send a professional email to me, you can earn some extra credit right away. And then here's the required course material. Okay, first of all, you need a computer. The software for this class does run on a Mac. So this is one of the few engineering courses where you can use a Mac if you want to. Usually the stuff only runs on Windows, but for some reason, the Texas Instruments people made software to run on a Mac. You're gonna need the textbook. So look who wrote this, me. Okay, so this course was designed and then the textbook was written. So we are gonna start on page 1. We're going to go to the end of the book. Everything that we're covering is in the book, and life is good. So Amazon is the cheapest place to get it. Click there, and it'll take you right to the link. And then you need your portable lab kit. Okay, so if you're listening to this video, you should have either emailed me your address to ship it to, or you should have swung by the ECE office in Bozeman and picked this up. We're going to demo our labs using just short videos and pictures and screenshots. So you need a camera, which is basically just your phone, but you're actually just going to take little 5 to 10 second videos and upload them to the assignment folders. So you'd be surprised at how much we can tell just by watching a short video of your assignment. So that's kind of a highlight of the overview. Let's go into the syllabus now and take a little bit more detailed look at the schedule. So click on this, and a lot of this we've already covered. So course description, outcomes. Everything we do in this class is for a learning outcome. So we don't just do activities because we can. We have a learning outcome. So it's a skill that's desired by somebody, like an employer, okay? And so just to let you know that. Contact information, here's links to our rooms again. This course starts on May 16th and it ends August 5th. And this is a fully online class. Content, what you need. Let's see here. Office hours. We're not going to have office hours because we're kind of always on call. Connor is, everything's so asynchronous now. It's not like 8 to 5 anymore. You just email Connor if you need to set up a video call, and he'll set it up with you. And then you can email as the preferred mode. You'd be shocked at how much we can answer over email by uploading, send us your code, say what's wrong, and we can figure it out. Grading distribution, the labs are king, right? So 60% of your grade are the labs. 300 is homework. The homeworks really are just about making sure you watch the videos. So they're really simple. They're really quick. It's just make sure you read or watch the videos and then prove it to us with the homework. So they're kind of free points. And then we have this big project at the end, which is worth 10% of your grade. The grading is straight letters. So 90 is an A. I don't give A minuses because I don't feel it's fair so that we don't have an A plus, and so I don't give an A minus. So if you get an 80, it's a B. If you get a 90, it's an A. Academic policies, the cheating rule is basically don't turn in other people's work. You are encouraged to work together, but we need everybody in this course to actually type out their own code, compile it, and download it to their own board. Don't ever just like email somebody else your code and have them upload it. Everybody has to take their own videos of their own boards working. But I do encourage you to work together if you are located near somebody. Course components, reading and videos are the same, right? It's the same content, so whatever mode works for you. The book, people have found that they really like having the book examples in front of them because I do a lot of example code in the book, and so you can kind of see it all at once as opposed to the videos. But the videos are me typing out a lot of code, and so it's kind of neat to see somebody actually doing it and showing what it looks like when it works. Homework. You're going to have multiple choice quizzes for homework. These are due at a specific time, and once the due date passes, the quiz is no longer available. So make sure you watch that. Then you have lab assignments, lots and lots of lab assignments, little short labs to show that you can actually program the MSP430 and make it do something. And then there'll be a final project where you can do something you actually come up with what you're going to do based on some guidelines, and then you fired off, okay? All right, this is the big one. This is the schedule. So you're going to notice it's given by week, so weeks 1 to 12, and it tells you what module we're working in, and every section of the book has a homework problem, and it has a set of videos. So as you go through these, you'll go through section 1.1 in the book, you'll have a homework, and then as you go along, you'll get to a point where you do a lab, okay? The deadline is over here, and the points are right here, where you have homework points, lab points, and project points. All the deadlines are on Wednesday at noon, okay? So the first week, you are going to have a couple short deadlines that are due on the first Wednesday of the first week. After that, we get into the flow where everything is due the following Wednesday at noon. So you're going to have a bunch of assignments that are due the following Wednesday at noon. You get to week 2, all the assignments are due the following Wednesday at noon. You get to week 3, they're due the following Wednesday at noon. And you'll notice that there's a lot of sections, but there are a lot of short sections, okay? And then once we get to week 2, at the end of 2, we start with another lab. Actually, you'll have one lab that's just getting the software installed, lab 1.1, and then we have lab 5.1, which is in module 5, and you actually just poke around with some of the software. Then we get into normal mode, which is a lot of short labs. So we cover sections 6, 1, 2, and 3, do a lab. Cover sections 6, 4, 5, 6, do a lab. Cover section 6.7, do a lab. And so you have 3 labs in 1 week, right? And you're like, that's crazy. Well, these labs aren't your traditional sit down for 2 hours. They're designed to be short labs that just give you stick time with the embedded computer. And we just keep going and going and going and going and going. This course consists of a whole lot of small assignments, and the total number of points possible is 1,000. So at any given point, you can see how many points you should have been able to earn and how many you've earned and figure out what your grade is, okay? But this is the big dog right here. Is you got to make sure that you look at this every week to know exactly what's going on. And I'll set an announcement out on Sundays that just as a reminder of it's like, here's kind of what we're doing, and rock and roll. All right, so that's the course. Let's look at an example. One last thing to look at is an example of what a content page might look like. And let me scroll down here to one that's got like labs in it. So I'm gonna go to module 6. So here's an example page. You come in here, module 6, data movement instructions. It's got our learning outcomes, and then it's got all the activities. So for every section 6.1, you're going to have a reading assignment or a video or both. And these videos are all just little YouTube videos. I try to keep them short. Sometimes it's hard when I'm coding, but you do those things. They're the same content, so whatever mode works for you. Then you're going to do homework. And the homework, when you click on it, it's a multiple choice quiz. So you come in here. Mine's a little different because I'm the instructor, but it asks you, do you want to start? And then it's just a couple simple questions on what is the new value of R8 if the following instruction is executed, okay? And I give you the figure, and you just come in here, plunk in whatever it is, and then when you're done, make sure to hit submit before the deadline, and you're off, okay? So that's just a whole lot of those, okay? Then you keep doing that. Section 6.2, read and video and homework. 6.3, read, video, homework. And then you finally get to a lab. So you come down here and you hit the lab description, and this will talk to you, this will tell you something to do with the computer. So it's going to ask you to do some sort of programming, make some registers or memory values be a certain value, and then you're going to show that off using a demonstration video or a screenshot, okay? And that's it. Then you upload everything to this assignment folder right here associated with the lab, and you're off and running. Since you upload something, Connor will grade it after the deadline, and you get your grade and you're off and running. But it's just like over and over and over. A lot of simple things, a lot of small points, and you just do a lot of them. And the whole goal here is to make it so that you are so comfortable programming this microcontroller that there's no fear or anxiety when we say, bring this microcontroller out and let's do something. You're just like, no problem. Plug it into your computer and you're off and running. The microcontroller, you plug it into your computer with a USB port. That's where it gets power. That's the communication interface to download your program, and that is how you run the debugger. And if you don't know what a debugger is, that's fine. That's what we're going to learn, okay? So that is the course. That's the course in a nutshell. And at this point, you should be able to start the course, start working through all of the assignments, know when they're due, know how to access them, and know what to do. And that is it. So good luck this summer. I look forward to working with you, and that is it. See ya.